Hello, this is the Tepid Coder. In this video, I want to talk about deques. So you imagine so far we've covered something like standard list T, standard vector type T. Let's move this over. Now we have something called standard deque type T. Let's recap these really quickly. Feel free to skim ahead if you already have a good understanding of all these. A list is going to need to allocate each node. As you make a new node, it just adds new connections, allocates new memory as it needs it, and eventually the last one points to a null pointer, and the one before the first points to a null pointer. So that's if it's doubly linked. If it's singly linked, there's nothing up here, right? Anyway, whereas a vector, you'll have something like no nodes, and you have one. Allocate 2 nodes, allocate space for 4 nodes. It doesn't have to be like this, but you basically allocate more space than you currently need in anticipation for the next node that you might be inserting. So you get some insertions for free. First one costs you, right? Second one, you have 2 now, still costs you, let's say. I'm just imagining it doubles each time. Third one, it costs you, but the fourth one doesn't because you got both these on the third allocation. So this one was free, I'll put an F here, right? And then you can imagine this doubling in size. So this one costs, right? But then these next 3 over here are all free. So vector is quicker for allocation, but there's also the case where if you always can't resize the block at the current address and it needs to allocate the block memory somewhere else, all of this needs to be copied to a new region of memory that's bigger, right? So you incur the cost of copying in elements, however big the list was at that point, or vector I should say. Whereas this one is pretty constant time for allocating nodes because you're always allocating the size of one node. However, traversing the vector and accessing an arbitrary element is much quicker. You just find the address where the vector is stored in memory, and you offset by n elements, which is basically n times the size of each element in the vector, and you jump right to that address. So that's pretty cool. Whereas with the list, you have to kind of start here, and then move forward, move forward, move forward. You're doing a lot of dereferencing, so bad cache locality, a lot of memory lookups which are slow. So this is really bad to traverse if you're looking for something. This is really good to traverse if you're looking for something, but it's also perhaps, what do I say? It's also slow to delete, right? With a list, when you want to delete something, you just make these 2 things attach and get rid of this, right? Constant time operation to delete. Really nice. If you want to delete a bunch of nodes, like if I want to delete both these at once, I could have just attached these instead. So if you're deleting a kind of range, it's pretty fast. Now for a vector, it's not really any slower to delete a range than it is to delete a single element, but it's still slow to delete the closer to the beginning of the list you delete. Let's say I delete the first element. What I'm going to have to do is push everything in the vector up. So I'm doing n-1 copies, where the length of the list is n. So, anything else I want to say about that? Constant time to create nodes of the list, but definitely slower because you're doing one at a time. Quicker to delete with the list. Okay, vector, quicker to allocate except when it has to copy any block, but that happens so infrequently that it's still usually way faster. Especially since you can reserve some number of nodes in a vector in advance. If you know like it's going to be at least 1 million nodes, might go over that a little bit, might not, you can start out with a huge number and just kind of get that for free. Deleting though, really slow. So, good for access, bad for deletes. Good for deletes, bad for access, and bad for allocation. Now deque kind of bridges the gap between the 2 of these. So the big problem with vectors, like I said, is deletion, but if you have a vector of a pretty small size, it's not that expensive to delete because you're not copying that many nodes over, right? So what deque does really is it just says never have a vector of more than n nodes, let's say. So you can imagine we have a vector of vectors is one way to look at it. There's a lot of ways you can implement this, but imagine you have like a block of nodes here, right? You have like 0, 1, dot, 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 n-1. Okay, and then you have another one of these, same thing, 0, 1, dot, 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 n-1. And then you have a bunch of these. So let's say dot, 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 over here, we have another one, 0, dot, 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 n-1. And in total we have m of these. So you could imagine we have something like a vector. And this doesn't even need to be a vector right here, because it's going to be constant size. It could be a vector of like arrays. Something like t, whatever. Some number in here, right? N. And this vector size is currently m. You have m nodes. Of course, you can't actually stick an array like that into a vector. You can put a pointer into it. It points to a block of memory. You could also give it a structure, which includes an array. So there's a lot of ways you can implement this. But essentially, you can imagine each of these just has n nodes in it, right? N nodes. And then as you need to add more nodes than you have room for in this block, you just allocate a new block inside of this vector. That's all that's doing. So one thing I did in the past to speed up list is I kind of took a different approach where I said I have a lot of things to load. It was actually a map for a 2D game I was making. And I had a tile editor, but loading the map was a bit slow after I added a lot of sprites when I was using a list. This is all written in C. So one thing I did was I said, okay, well I have a list of nodes, which have like a structure where you can point to like next. You can point to previous. Okay. And you have some kind of like, I don't know, let's say void star data. You know, whatever stuff in here. So instead of having this point to a bunch of new nodes in memory like this, what I thought I would do, this is pretty similar to a deque, is I said, why don't I just allocate a bunch of nodes at once in a giant block? They're still going to point to the next one, but the next one that it points to is just inside of this block. And then whenever I want, I can just insert a new block full of like n nodes. And it'll just check to see if there's room in that block to do any insertions. So if there aren't any nodes in the block that are free, then it has to allocate a new node, right? And I would just do single insert from there, or I could do another block of nodes if I so choose, right? So basically in this case, I had a flag saying that this list node is actually in use or not. So that was pretty nice. I could reuse nodes inside of this block, which is kind of cumbersome, but not that big of a deal. But really this idea of a vector of vectors I think is a lot better than what I had done there. Not by a huge margin, but the big drawback of this method was having to reuse these nodes. I had to essentially keep a list of free things, whichever nodes were recently deleted and could be reused before allocating something new. So I wanted to maintain insertion order when I'm iterating through it, then I couldn't actually take that approach. I'd have to just kind of like abandon this node and lose that slot in memory. Or I'd have to shift everything up, right? And then I'm incurring the same cost that a vector would. Anyway, let's not think about that for now. But I only brought this up because of the rationale of why you might want to put things in a block and make things quicker to allocate, which is kind of what vectors are doing under the hood anyway. So yeah, I drew another picture here in advance. So this one right here. Imagine we have a linked list of nodes, and you want random access. So if we just wanted to speed up the list to have random access, we could say, you know, list position n, and get, you know, the nth t, right, from that. That's supposed to be an ampersand, but, you know, trying to draw with the mouse here. Anyway, if I wanted to get that, I could iterate the list and just return the nth node, but that'd be slow. I could also have a table of references to each of the nodes in the list. So on top of having like a next node and a previous node pointer, I could have a table of pointers to these nodes themselves, right? And just for fun, I put an ID here, like this would be ID 0, this would be ID 1 for the node, ID 2 for the node, just to show that it kind of like relates to the index of the lookup table. So one thing you'd have to do though, if you had this kind of node, like you have some kind of system where there's things you need to reference by ID, and you have to do lookups, you might want to make it so that these two things stay in sync. In that case, you could say if you want index 0 to stay relevant to the index here, as you delete nodes, you would need to decrement all of the values after the one deleted. So this is 0 right here, this is 1, and we deleted 0. This 1 would need to become a 0, and this 2 would need to become a 1. You have to decrement that. And I kind of show that here. How, like, if you deleted the second element, which is index 1, you're going to get this 0, 2, 3, 4. So you have to decrement them and get 0, 1, 2, 3. Okay, and then we have also the number of nodes we need to copy over inside of this table in order to keep it in sync. For deleting 0 is going to be equal to the size of the list minus 1 in that case. But in general, it's going to be the index of the element after the one that you're deleting subtracted from the final index in the list, which is the size of the list minus 1, and then plus 1 because it's inclusive. So if you're imagining we have something like, I don't know, b minus a, let's say b is 5 and a is 3. That'll give us 2, but if you want this whole range, 3, 4, 5, right, that's actually 3 elements, not 2. So it's that plus 1. That's where that's coming from. So in this case, the start right here, last element of the list, that index. And this is the index after the one you're deleting, that plus 1 to get the entire range of elements. So for deleting 0, it would be this whole range here, not this range. Okay. When I say I didn't mean deleting, I meant once we're copying upwardly, moving this here, moving this here, moving this here, moving this here, and so on and so forth, all the way until we get to here. Anyway, in this example, I show that I'm deleting index 1, which is the second element, which means I have to push 3 elements back. And then I have to keep them in sync by decrementing the ID field of all of the nodes past the one I deleted. That's only if I stored this. And obviously there's no reason to have a previous pointer and a next pointer if I have a table of, you know, node pointers anyway. So let's go down a little bit. So imagine we have our vector here, and then we have a table, which is also another vector, right? This vector would just store pointers to vectors. So the pointers that this hold are pointers to these vectors here, which have blocks of nodes. So you imagine you have, like, this is a vector of type t, whereas this would be a vector of type t pointer. That's probably how I'd implement that. Okay. Now, I wrote here quicker allocation than list, which is true because we're allocating in nodes at a time, always. Whatever you define in to be for the size of this vector, right? It's quicker for deletion than vector. And that's because as the vector grows, if you delete the first element, right, you're going to have to copy over in minus 1 nodes, where in is the length of the list, if I delete the first. Or if I delete the last, I don't have to copy any nodes over. So it's kind of unbalanced on how quick the deletion speed is. You could have 10 million elements inserted into this deque with this implementation, but it would be broken into, let's say, m blocks, right? Block 0, block 1, block whatever, of each having in nodes. So when you delete, at worst, you only have to copy over in minus 1 nodes, right? So n minus 1, which is however many nodes you have in each of these blocks, so each of these vectors here. So the other thing too is, it's quicker than list to do access to any given node. That's what I mean by quicker than list. So say I want the xth node in this deque. What I could do is I could say floor of x divided by the number of nodes per block, which in this case would just be, I have n nodes here, right? 0 through n minus 1, so x over n. And we're going to floor that. And we'll use this as the, let's say I equals I. So I'm going to look at block I, and then from there I'm going to offset whatever the remainder would be. So this gives me something like a t star, so a pointer to type t. It's like an array of t's, really. It's like a vector which has a subscript operator overload, but I can kind of treat it just like a t array. Anyway, from there, let's say I have, this gives me some, I can't call it m, what can I call it? Let's call it node pointer, right? So from there, I'm going to access node position. It's going to be x mod in. There we go. And that should work. Because if I divide this element index that I want by the number of nodes in each list, that'll give me the block that I want. Right? Say I have 10 in here, and then 10 in here. That means this is going to be 0 through 9, and this is going to be 10 through 19. Okay? And say I want element 12. Well, if I do 12 over 10, and I floor it, that gives me, well, 1. Okay, and then if I do 12 mod 10, that's going to give me 2. So, would that be right? 10 to be the first element here, and I'd have 11, 12. So yeah, 10 to be 0, and then 1 and 2. So that would be the 12th element. 9th is right here. So yeah, that's right. So that's how I'd access it. I'd basically look at the vector of vector pointers, right, inside here, and I would get the index of this table that relates to the requested node index divided by the number of nodes per block, and floor it. Okay, that would give me this 1, and then I would use the element index they wanted mod that number of elements per block in order to get the element within this, which would be this 2 right here. So that should work. So that's very quick for lookup. I basically do one lookup, address of vec, and then 2 offset of vec. I have to find this address. That's a lookup within the table. And then I guess there's a lookup offset from that address that I get from that lookup. So that's basically what's happening. And that's really fast. And if I delete, it's only ever going to be, you know, up to n-1 nodes. n-1 because if we delete the 0, then there's n-1 left, whereas before there was n. So all these have to be pushed up. So this helps us by reducing our worst case deletion time. It also improves on standard list by, what do I say, allocating n times faster, because you're always allocating n nodes at once. It wastes a bit of space, whatever n is. n-1 nodes are going to be wasted if you don't need them for each new block allocated. But it's a pretty nice compromise, and I use deques all the time if I want quick deletions. So I'm going to show an implementation of this in the next video, and I think I'm going to probably implement it with my own ghetto vector implementation that I was starting earlier, and just stick 2 of those into a class as dependencies, and build upon it that way. Because I think just using standard vector to implement this would be kind of cheesy. It wouldn't be too interesting to watch. I don't know, maybe your opinion on that varies, but anyway, if you got something out of this explanation, give it a thumbs up, consider subscribing for more content like this, and if you have any questions, comments, suggestions, I'd like to read those. Anyway, I will catch you guys later. Happy coding.